The so-called MM1 model is one of the most popular analytical models for analyzing a single waiting line. That means that the MM1 model is essentially a set of formulas. Each formula answers a different question about a waiting line. So the challenge of using the MM1 model is recognizing which formula answers what question. This particular question is a good chance to practice that. Customers arrive at an average of 10 an hour. All right, that's important. That is lambda, the average customer arrival rate, 10 per hour, and an average of 16 customers can be served in an hour. That is equally important. That is mu, the traditional symbol for the customer service rate. We can't go any further with this thing called the MM1 model until we have an estimate of lambda and mu. There'll always be numbers of customers. The number of customers that on average arrive in a certain time interval, here's it's an hour, and then the average number of customers who could be served in that same time interval. It is important that those two things match. Okay, well they do, so we're ready to continue. Assuming this is the MM1 model, and that's our assumption this whole time. The average amount of time spent waiting in the line. That's a formula. Okay. The average amount of time, it's going to be capital W spent waiting in the line, capital W sub Q. Q is another word for line, so wait in the line. What is that formula? That formula is LQ, the average length of the line, divided by lambda. Oh, okay. So in order to answer this question, the average weight in the line, that means I have to first calculate the average length of the line. Yes. So the formula for, if you wanted to like tack it on here, the formula for the average length of the line is lambda squared, that divided by mu minus lambda. All right. So you would have to back up, find that formula for LQ, and calculate it first. Now, I've done that. LQ for this particular problem, if you say 10 squared divided by 16 times 16 minus 10, 1.04 some odd, basically. Oh, okay. Now the thing that I've been after this whole time was the average weight in the line. Now that part is actually easy because I just say WQ is that, the average length of the line, divided by lambda. Oh, divided by that 10. Okay, did that. Average weight in the line, then that becomes 0.104. That's the average weight in the line. 0.104. Okay. Now, this is the answer. It's not wrong. It's important to be able to interpret the answers to some of these formulas. This is, like how much time actually is this? What is the average weight? This is 0.104 hours. How do I know that? Whatever lambda and mu originally referred to, your answer to this formula will be in that same time interval. So, 0.1, basically a tenth of an hour. You may want to translate that into something more intuitive, and it's very easy. For instance, if you wanted to translate that to minutes, you would just say 0.104 times 60, because there's 60 minutes in an hour, which reveals that basically it's about 6 minutes. And if somebody was asking you what was the average weight, in that particular system, that probably would be a more intuitive response. And so 0.0104 hours, no, it's about 6 minutes wait. Okay. Now this next question here looks like it is actually about the same system. And the reason is because it's the same lambda and the same mu. Customers arrive at an average of 10 per hour. Okay, lambda equal 10 per hour. It's the same. and the average 16 customers can be served. That's the same mu of 16 per hour, assuming it's an MM1 model. That's what we're talking about. What is the average amount of time a customer spends in the system? It's asking after a different formula. The average amount of time a customer spends in the system. Now wait a minute, how's that any different from what we just calculated? The about 6 minutes? That's on average how long they wait in the line. Okay, the total amount of time they spend in the system includes being served. So, usually abbreviated with a capital W because it's still a delay, a wait, but sub S meaning system, the whole thing from front to back. How do you calculate that? Well, the formula is WQ, how long they wait in the line, plus 1 over mu. Okay, so I'd take that 0.104 from, where I was working up here and calculated WQ. There's them waiting in the line, plus 1 over 16. I get 0.167 then. Okay, and I remember that that's hours. So if somebody asked me, this particular system on, overall, how long does it take? How much time do you spend there? It's 0.167 hours. Again, probably not that's a correct answer, but probably not a very intuitive response. Multiply that times 60, for instance, and that reveals that, oh yeah, that's about 10 minutes. This particular system, with this amount of people coming into it, working this fast, generally takes you about 10 minutes to get in there, wait, get served, get out of there. All right, now, oh, wait a minute, the next question looks like it's the same system. Customers arrive at an average rate of 10 an hour, and they're served mu at an average rate of 16 an hour, assuming the MM1 model. What is the probability of no customers in the system? That is another formula. We can recognize it if it's listed capital P for a probability. It's asking for chance. Sub-zero, meaning probability of nobody or nothing, 0 people there. That is, it's pretty simple to calculate. It's just 1 minus lambda over mu. Oh, all right, just fill it in. 1 minus 10 over 16. I get 0.375 or 37.5%. Okay, so what does this mean? It means there's a 37.5% chance that at any given moment there's nobody in the system. Okay. That also means that this system is idle 37.5% of the time. That also means, or is the equivalent of, the chance that you have, if you turn up, of being served immediately. The probability that there's nobody in the system is the same thing as the chance that you could be served immediately if you chose to show up.